Okay, let's talk a little bit about the homework. And because the modules coming up are going to be different from the ones that have come previously, namely that we're going to focus on code wars rather than learning about additional data structures, I want to do a little bit of a sum up of the modules so far, just in case you're worried that you are missing a high-level detail or the big picture or something like that. Now that you've implemented the same classes, decks of cards and taco trucks, several different ways with different underlying data structures, I want to just sum up some of the concepts there so that you'll be able to remember the big picture even after this class is over. But first, let me go over one thing that I think many of you struggled with in the last homework, and it was specifically bullet 4 in the README. So I'll open up the README here. This asks you to refactor the orders test file to run the list orders impl file as well as the orders queue impl against the same criteria. Note that as both use the same interface, you can test the logic with the same method. So there's a lot to unpack here. And the first thing I think you really should know, like if you want to commit an important word to memory, refactor is one of those important concepts in programming. Let's just Google it, in case you don't believe me. So refactoring is a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. That's the technical definition. There's a whole Wikipedia article about it that is probably worth skimming, at least. Here it's asking you to refactor the orders test file such that it's capable of doing something new, as well as what it was previously doing. So let's pop over there and see what it was previously doing. Here's orders test. Previously, it was running two different tests. Test has next false and test close next order, and both of these test orders queue impl. Let me do a quick refactoring of this code where I will stick to this very strict definition, restructuring an existing body of code, altering its internal structure without changing its external behavior. So without changing its behavior, I'm going to change the code. It's a little bit of a weird idea. You're going to change your code, but you're not going to change what the code fundamentally does. So here's an example of a refactoring. I'm going to refactor test has next so that it doesn't have embedded inside of it the particular orders implementation that it is testing. And the way that I would do that is to lift this into a parameter. So I will say orders, got to spell it right, orders. Notice I'm just taking this variable here that's defined locally, and I'm saying it's going to now be a parameter. So I will now extract that. And of course I get an error up here. And so now I'm going to pass it in. I'm going to pass in a new orders queue impl. Now this test will do the same thing it did before. If it was passing before, it will still pass. If it was failing before, it will still fail. The behavior hasn't changed, but it does now have a new capability. Now this test has next false has the flexibility to take in anything that implements the orders interface. So I'm passing in the orders queue impl because that's what it was testing before, but you could now pass in a different one like orders list impl, assuming that that exists. It would in your homework, because many of you were able to do this no problem. You made an orders list impl, you used a list as your underlying data structure, and you implemented the orders interface. So that for many of you was not a tricky thing, but I noticed that the struggle came in bullet point 4, where very few of you refactored your orders test file so that you could run both of them. I did see a lot of something else. This is kind of the non-refactoring way to do it. Let me go back to how it was before. And I gave you full credit if you did it this way. is just not the best way to do it. So let me show you what some people did. You took the whole function and duplicated it. And then you renamed it to maybe test has next false list. And then you changed this one tiny part of it. And that works. That does work. You know, if you call one, then call the other, it accomplishes the same goal. And since this is just Java 2, I didn't take off points if you did it that way. But if you do it that way in industry, other programmers will notice it, and they will tell you to do it differently. And the reason is that there's a concept called DRY, or dry. I'll Google it here. Dry coding. Dry is an acronym for don't repeat yourself. And there's a whole Wikipedia page about it. It's a principle of software development. Generally speaking, when you're coding, if possible, you want to try to accomplish your goals with as little code as possible, and definitely without duplicating large chunks of code. So even though this does work, there's a better way to structure it that avoids all of this duplication. And different people solve this in different ways. Not everyone duplicated the whole method. Some of you duplicated the contents of a single method, but it was the same idea. Your code got considerably longer. So if instead you do what I did at the very beginning, where you refactor this test to take in the order that is to be tested, then it becomes flexible enough that you can use it multiple times for different orders, for different order implementations, without having to duplicate any code. All you do is duplicate the calls to those methods. So you end up with a lot less code. It's much cleaner. It's more dry, and it's a better solution. So that's concept one. I wanted to go over that. Secondly, I wanted to try to draw a picture of some of the ideas that have come up implicitly in the homework. Let's look at the taco truck example. So you have actually built, at this point, several implementations of a taco truck that takes taco orders. And the idea is that somebody walks up to a taco truck, then they can interact with that taco truck via the taco truck's interface. So that in Java would mean something like calling a method like add order. And then they add their taco to the order. Now inside the taco truck, that's where the implementation happens. Now from the perspective of the person using the interface, that person doesn't have to care about what is inside the taco truck. It's a complete black box. The implementation of the taco truck is hidden. And that is a benefit to whoever is running the taco truck, or in this case, whoever has written the taco truck orders impl class. It gives that programmer a lot of flexibility. So let's say inside of the taco truck you have a queue to which orders are added, and you implement that queue as a deck, as a Java deck. Cool, that works. There's nothing wrong with that. Person outside doesn't have to know that a deck is getting used, and that's fine. And what that means is that you can have alternative implementations. So you might have queue as an array list, which you also did. You could have queue as a hash set. Although, I will point out, it's actually a little tricky to implement as a queue as a hash set. But we'll come back to that. My point is, you can sort of think of this exterior, this square that I've drawn here, as the surface of some machine, the hood of a car, for example. And you can swap out the insides. So I could swap out and say, okay, well, now let's implement the queue as an array list. Person outside doesn't have to care. The code that interacts with the taco truck doesn't have to care. All they're doing is calling add order. And again, it does not matter one bit to them whether inside the taco truck, beyond the interface, it's implemented as an array list. You can swap that out for a deck again. Again, no one has to care except for whoever is maintaining the taco truck class. You could do it as a hash set, perhaps. It's a little bit like taking an existing car and swapping out its engine. You still drive it the same way, still got a steering wheel, still have a brake pedal and a gas pedal. The interface from the perspective of the user is the same, just swapping out what's under the hood. And Java makes this easy because you structure your code as classes, and within those classes you're allowed to make certain things private and protected so that the users of that class, whoever instantiates your class to make objects, they just call methods on it and they don't have to know about what's happening underneath. So if you're wondering why did we do so many examples of a taco truck with so many different data structures, one was to give you a kind of survey or tour of different data structures so that you'd be able to call to mind the idea of an array list or a deck or a hash set, so that you'd know that there are these different data structures and that they can sometimes be used to accomplish the same task. My last video, I showed you that sometimes, depending on the task, there are trade-offs between certain data structures. There might be certain operations on, for example, an array list versus a linked list that are faster or slower, depending. My example last time was that adding onto the end of a linked list actually takes longer than adding onto the end of an array list. And so depending on whether or not on the inside of this taco truck you want to add onto the end of some list a lot, then maybe you might swap in an array list, or maybe you might decide that actually the better engine inside this taco truck is a linked list. In which case, you could decide, let me not use the array list. I'll use the linked list as well. And big picture here, the big idea is that by creating these classes with these interfaces that don't change, you get the flexibility to change other things without breaking other code. So you can swap in a different implementation while maintaining the same interface. I think that's the big picture. If there's any kind of big concept in object-oriented programming that you should try to remember, it is that one. It is that idea that interface and implementation are separate. Interfaces, we want to try to keep the same because if you change that, it can break other code. If you decide taco truck no longer has an add order method, or you decide even something simple like you want to have the A in add order be capitalized, you have to go change every piece of code that's calling it, every single one. It breaks it. It might not even be your code. Maybe you created the taco truck class as a library and other programmers are using it, and now by changing that library you just broke all of their code. They have to go update it. So changing the interface can have effects that ripple out and affect other pieces of code that you've written or pieces of code that you haven't written, that somebody else did. Changing interfaces can be a frustration. So if you can create some interface that stays the same and only change the implementation, that is preferable. When you can do it, that is preferable. Now, I'll circle back to one thing I said earlier, which is what if you stick a hash set in there? Can you implement a queue as a hash set? Well, we can do it with an array list, we can do it with a linked list, and we know we can do it with a deck. These three are viable engines that you could put in as implementations for your taco truck. But let's look up a hash set. So a hash set, here we are on the docs page, implements the set interface backed by a hash table. a hash map instance. And this is the thing I wanted to point out. It makes no guarantees as to the iteration order of the set. What that means is a hash set is a collection of things, just like an array list, just like a linked list, and just like a deck. So it's similar to those things in that way, but it is different in one important way, which is that the order is undefined. It's just like a kind of bag of things, not like a nice ordered list of things. So implementing a queue, which is first in, first out, where the order matters. Like the whole point of a queue is that the order in which things come out is defined by the order that they go in, first out. That concept is all about the ordering. So implementing something where ordering matters on a data structure where ordering is undefined is tricky, and in fact not theoretically possible. It's not theoretically possible to do that with just a hash set. So I think that's a little bit of a gotcha in Module 4, where you're asked to do that. So two possible solutions there. One, by the way, just so you know, I'm not going to take off points if you got it wrong, because homework is asking you to do something that's not theoretically possible. So your guess is as good as mine about what the right answer is there. But two things I think are good ways to deal with it. One is that Java does have something called I think it's called a linked hash set. A linked hash set is also a set. In fact, it's a subclass of hash set, but it does have predictable iteration order. So that would be perfectly fine. That's an okay data structure to use. I'll put that on my list here. Say that a queue as a linked hash set would be fine. So if you wanted to swap that in and use that as your data structure, that's okay. That will work. You do have predictable iteration order there. Another one would be to use some combo. Maybe you use a hash set as your storage, but you track the order that things are in the hash set with some other data structure, like a linked list. You can use a combo of a hash set and a linked list, which is probably what linked hash set is, actually. If we looked at the implementation of linked hash set, probably doing something like that. So that would be another possible thing that you could do if you really want to get your homework precise. But if you try to implement a queue as a hash set, you might get the tests to pass. But if they pass, you're just getting lucky, because in a hash set the order is not defined. Not defined means it might come out in, first out order, but it also might not. So some of you might be like, wait a second, I used a hash set and it worked just fine, all the tests passed. Well, sometimes tests pass, but implementations still aren't quite correct. So bear that in mind. And add it to your list of trade-offs between different data structures. Array list, linked list, and deck all have an ordering defined on the elements in the collection. Hash set does not. Linked hash set, though, does. It comes to the rescue if you really need a hash set for some reason and you need ordering. So we've seen several data structures in this class. It's only been a few short weeks, but we've toured the land of Java data structures for quite some time now. And now though, it is time to pivot and focus on the other aspect of coding, which is algorithms. So for that reason, the rest of this course, we're going to look at code wars, and we're going to solve some coding problems that will help you get ready for your interviews one day if you're interviewing for software engineering positions, and it'll help show the other side of coding, which is algorithms rather than data structures. Most of the problems in code wars at the level that you'll be tackling for your homework will deal with very simple data structures like ints and strings. As you get higher up in code wars, that is when you might start to see problems where it's required that you use the right data structure. Because if you don't, your solution won't be fast enough. And that's usually where it comes in. That's where, like, this data structure, it's hard to get a feel of which data structure is right and when does that matter until you see algorithms where it makes a big difference. So if you come across some higher level code wars problem where you tried to solve it with an array list, but it's not finishing in time because the tests are testing your code with, let's say, 1,000,000 operations, then that's the case where you might have to say, okay, I got the algorithm right, but the data structure is wrong. Swap in the right data structure, and then everything works. So as you practice your Java skills, all of this will come together. It'll loop back around. But in this class, you probably won't get to a high enough level in Code Wars where you see these particular data structures come up in your problems. But it is just one class, Java 2. We have a lot to cover. So trying to give you the big picture here and equip you with tools that can help you continue your Java education once this class is over. And in my opinion, two biggest ones are Code Wars and other sites like it, and just the Java documentation itself, being able to read through essentially the instruction manual about the interface for these various data structures. That is where a lot of your learning will come from. So with that in mind, as always, feel free to reach out if you have questions about object-oriented programming, about the homework, about Code Wars, or just about what it's like to be a programmer, or what the software engineering industry is like these days. As always, I'm here to help.